Okay. Share screen. All right, so we're going to go ahead and start with announcements. So if you go to the announcements and CAT courses, the material that we're going through right now is really hard because they're assuming that you already have all of your amino acids memorized and that you have like their charges, pKa values, all you understand all that stuff, what the pKa is, like everything. And if you don't, then you're going to struggle with the material because you have to stop and then remind yourself of what it is, look through your notes and stuff. So it'll really slow you down. So hopefully you're like memorized. And I'm going to go through it really slowly because this is the kind of material that makes your brain hurt. Okay. So I also uploaded 3 videos for you guys. Okay. 3 videos that I'm really proud of because I explain things like really well. I prepared these not in Drawboard PDF, but PowerPoint, and it allows me to color code your definitions that I give you. So it'll be like red with black for emphasis, or tiny like definitions will be in black. So it's just like a lot easier for a student to like follow what it should be emphasized and stuff. I can't do that with Drawboard PDF. So check out the videos. One is chymotrypsin, one is everything to do with KM, the different types of inhibitors, the types of graphs that you'll see, all the stuff that will be on your next exam is in like these videos. There should be more videos, but I mean, these are like concepts that students really struggle with. So that's why I posted these. And then another one is you haven't started learning that yet. So, but you will probably next week. So those videos are there. I also created a playlist for this class on YouTube, and there's like 13 videos in the playlist. So these 3 are a part of it. So then we can talk about lecture 12. So most of lecture 12 is about one enzyme, and that enzyme is called chymotrypsin. So what does that tell you if there's almost an entire lecture on one enzyme? Maybe learn it like really, really well. So that enzyme's name is chymotrypsin. And then towards the end, you have 2 other enzymes. You've got enolase, and then you have hexyl kinase. So this lecture 12 is about 3 enzymes: chymotrypsin, hexokinase, and enolase. So you should learn all 3, but mainly focus on hexokinase since, you know, it was like 20 slides or something. Okay. So now, actually, I wanted to see if this was working. Something's up with my YouTube. It's looking weird. I don't know why. But basically, look at these beautiful notes for chymotrypsin. I give you all the definitions and everything that is happening, even in bold. Everything in bold, those are your terminology that you need to have memorized, because those terminology will be used on the exam. If you don't have it down, you're not going to know what to answer. So this is what I mean by knowing the material backwards and forwards. So watch the video. It's only 15 minutes long. And then let's get started on our worksheet for today. Okay, everyone on Zoom, make sure you put here in the chat so I know that you're here. And then we'll get started on our worksheet. Pay extra attention. This stuff is hard. So I'm going to be very repetitive and I'm going to go through it very slowly today. All right, so you're going to have to know, I don't know if you remember last week, I taught you how to make a Lineweaver-Burke plot. A Lineweaver-Burke plot. So let's go over it really quickly. So you have the y-axis and you have the x-axis. And this is where we inverse the normal stuff for the Michaelis-Menten plot. So the x-axis is 1 over the substrate concentration. The y-axis is 1 over the V naught, the initial velocity, okay? So remember, the line goes down and to the left. You can have negative values here. Remember that there was 2 things that were really important. Whatever crosses at the x-axis and whatever crosses at the y-axis. So whatever crosses at the x-axis, that is your 1 over Km. Whatever crosses at your y-axis, that is your 1 over Vmax. All right, so you have to be very familiar with the Lineweaver-Burke plot because you have to know, you have to have these 4 memorized. So I went ahead and put them in here for you with all the information that I could find on the 4. Should only take about half an hour. Practice drawing them on a whiteboard. Basically, you're using inhibitors. There's 4 different types of inhibitors that you can use to block your enzyme. And so you have to learn when you add this kind of an inhibitor, what does it do to the Vmax and to the Km? So you can see here, no inhibitor in the black line, okay? And then when you add the inhibitor, you see for this competitive type of inhibitor, when you add the inhibitor, the y-axis, whatever crosses there, does not change. The y-intercept does not change. But the x-intercept, wherever the Km is at, that changes. And then I summarize that for you here. Km increases. Vmax doesn't change. Okay? Now, the Km increases because remember, the Km is negative right now, and if it moves to the right, it becomes more positive, so it's increasing. Okay, so you just have to memorize these 4 and memorize like what they do, and then I even put the definitions for you down here. And then we also have something called irreversible inhibition, and that's when you have a type of inhibitor that does one of these 3 things, and then your enzyme won't work anymore. But for these 4, we're talking about reversible inhibitors. And then I give you all the definitions down here. Okay, so I'm going to let you memorize that on your own. And we're just going to get started. You measure the initial rate of an enzyme reaction in micromolars per second. So remember, what they're giving you here is V naught, because they're saying, at this point, you have to start plugging things in by yourself. You measure the initial rate of an enzyme reaction. So we know initial rate is V naught. As a function of substrate concentration, we know that substrate concentration is on the x-axis in the presence and absence of an inhibitor. So basically, they're going to give you a table with some data. You're going to find some stuff, and then you have to figure out what type of inhibitor they gave you. Okay, so we're going to walk you through the whole thing. It's actually super easy. Okay, all right, so they want to know the Vmax without the inhibitor. Well, let's look at what we have here. We have, oh, it's really slow, sorry, substrate concentration. Then they give us V naught, initial velocity, with no inhibitor and with an inhibitor, okay? So now, they want us to find the Vmax with no inhibitor. Well, that's easy. Vmax is maximum velocity, bam, 102. Is that easy? All right, let's find the Vmax with the inhibitor. You just go to the highest, bam, it's still 102. So the Vmax does not change for this type of inhibitor. Now, they want us to find the Km with and without the inhibitor. Remember, I was going to ask you what the Km is, but I don't need it. I'm just going to tell you. The Km is the substrate concentration at half of the maximum velocity. The Km is the substrate concentration at half of the maximum velocity. So the maximum velocity was 102. So about half of that is 52. But 52 is not the Km. A lot of students lose points because they're like, oh, it's just half the maximum velocity. No, no. That's half the maximum velocity, but the Km is the concentration. So you have to go to the left and look at the concentration column. This is substrate concentration. So if you go to the left, this is our Km. Our Km is 0.0002 micromolar. Easy? Okay, because you know your terminology and you have a good foundation. So then it's easy. If you don't know your terminology, you're not going to do well. Okay. All right. So for the inhibitor, now we're going to go find half the maximum velocity. Again, it was 102, so it's still 52. So we got to go to the left to get the Km, and the substrate concentration is 0.0005 with the inhibitor. Easy? Okay. All right. So now they're asking us, what kind of inhibitor is this? So I'm just going to walk through the answer with you. So notice that the Vmax didn't change, but the Km did change. So this is a competitive inhibitor. We just covered it in this graph, competitive. The Vmax did not change. So the y-intercept did not change, but the Km, it did change. And you can see that on the x-axis. This is why it's so important to have your Lineweaver-Burke plot memorized, okay? All right, now, okay, so here's a harder one, but you've got this. Use the estimated Vmax and Km values and the Michaelis-Menten equation to calculate V naught when, so they're giving us a substrate concentration in the absence of inhibitor and in the presence of inhibitor. So this is super easy. We already have all this information, so that's how we know that this is the formula that we're supposed to use. V naught is equal to Vmax times the substrate concentration divided by Km plus the substrate concentration. So this is just the Michaelis-Menten equation, the basic one. Okay, so we have everything. So I set up this first problem. It says no inhibitor. So everything is the same except for the Km. That was the only thing that changed. So let's go look over here. Let's make sure we know how to plug this in. So Vmax was 102. The substrate concentration, they just told us, was 0.0004 divided by the Km. So without the inhibitor, our Km was 0.0002. And then plus the substrate concentration again. Is that easy or what? Okay, so the answer is 68 micromolar per second. That's our V naught. Again, V naught is initial velocity. Okay, now it says with the presence of the inhibitor. So again, we just set up our problem exactly the same. The Vmax was still 102 because our Vmax didn't change. The substrate concentration they said was the same, 0.0004. And then you divide that by the Km, which that's the one thing that did change. So our new Km was 0.0005 plus, and then we just do the substrate concentration again. And that equals 45 micromolar per second. Easy? Yeah. So somebody send me an email and I'll try to remember to upload this for you guys today. Like right after this class. Actually, I'll just try to do it right now, right after this class. Just like remind me. Okay. No, they can give you nanomolar. Yeah, you just have to really pay attention. Yeah. Okay, draw a Lineweaver-Burke plot for each of the following inhibitors: competitive, uncompetitive, non-competitive, and mixed. Explain the effect that each kind of inhibitor might have on Km and Vmax. So I I put all those notes for you up here along with the graphs. Just memorize them. If you need somebody to walk you through each step, the video is already up there as well. This is like, I think it's the third video that I linked, okay? All right. Chymotrypsin, finally, oh my gosh, here we go. Here we go. Chymotrypsin, this is probably what we're going to talk about for the rest of the discussion. Chymotrypsin is an enzyme that catalyzes the hydrolytic cleavage of the peptide bond after large hydrophobic residues. All right, that's a lot of terminology. Chymotrypsin, let me stop sharing my screen because you guys got to see the board. Okay. Chymotrypsin is just an enzyme. Okay, I'm going to simplify it for you. It's just an enzyme. And if you guys remember, when you have a polypeptide, you can have like a bunch of amino acids. Okay, bunch of amino acids. And what do amino acids do? They hold hands. They hold hands, and wherever they're holding hands, that's a peptide bond. So it's NCC, NCC, NCC. So remember, this is the amino end of a, amino acid, alpha carboxyl. That's where the R group is gonna go. And then we have the carbonyl, and that is holding hands with the amino group of the next amino acid. And this is the peptide bond. So NCC, and then that's another peptide bond. You guys remember that? Okay. So now, the rule for chymotrypsin is that, this is the rule. This R group has to have a phenyl. Whatever, it's gotta have a circle, okay? It has to have that. And we have 3 amino acids that have that. So that has to be there in order for chymotrypsin to break this peptide bond. Now it's talking about hydrolytic cleavage. What is that? Hydrolytic cleavage. Well, that's just when a water molecule goes in and breaks a bond. Hydrolysis. Hydro is water, lysis is breakdown. So this is all these concepts, those big words that we just read. Chymotrypsin is an enzyme that catalyzes the hydrolytic cleavage of the peptide bond after large hydrophobic residues. This is what they're saying in all that terminology. Make sense? Kind of? It's all terminology, but I'm recording this so you guys can rewatch this if you need to. Okay. So what else do I need to tell you? Okay, we can get started. We can get started and pay extra close attention because now we are talking about chymotrypsin. I'm going to be very repetitive. Okay, so now I can share my screen again. Okay. So chymotrypsin looks like this. This is the active site of chymotrypsin. Okay, right here. All that stuff going on, I'm going to explain it to you. I'm going to break it down. Okay, then what goes inside of chymotrypsin is the substrate, any polypeptide. But there's our rule. We got to have that phenyl group right there. Then we have the carbonyl, and then we have the NH of the next amino acid. And this is where that peptide bond is going to break. Whenever chymotrypsin breaks this bond, it kicks this blue guy out. And now he is product number 1. And then later on, this is where hydrolytic cleavage will come in. The water molecule will come in and detach this part from the enzyme and kick it out. So now we'll have product number 2. So chymotrypsin is a 2-step process. The first step is to break this peptide bond. The water molecule is not used to break that bond. I'm going to tell you about that right now. The second step is to detach this portion of the polypeptide from the enzyme and release it. So that is where the water molecule comes in to break that bond. So they might try to trick you on an exam and be like, oh, hydrolytic cleavage happens at step 1, and that's what breaks the bond for chymotrypsin. No, that is not what happens. The water molecule comes in after, in step 2. Step 1 is where that peptide bond breaks. And I'm going to tell you how it breaks right now and who breaks it. Okay? All right. So this is the active site for chymotrypsin. We've got a few elements here. We've got the hydrophobic pocket. Who goes in the hydrophobic pocket? Why is that pocket there? The phenyl group. Yeah, the hydrophobic pocket is there for this phenyl group. That's where he's going to be hanging out. I don't really know. They did include him in there, but I'm just like, I don't really know. I haven't come across that. That's a good question for the professor. Okay, so then we have this other element, and it's called an oxyanion hole. Well, what goes in here? Yeah, so this specific carbonyl, the one attached to the peptide bond, that's the one that's going to go and fit in the oxyanion hole right here. And it's mainly the oxygen that fits in there. Okay, so we got it. Hydrophobic pocket. That is where our phenyl group is going to go. And then we have the oxyanion hole. And that is where our oxygen from the carbonyl from the peptide bond is going to go. Now, we have a couple of amino acids here in the backbone of chymotrypsin, and those guys are pretty important. They remain in that location. They can't move. And if you can see here, the NH, each of them has their amino terminus. So you just know the N portion. So they're both showing you their N portion with the hydrogen bond. What do we know about hydrogen bonds? They tend to have a positive charge, like a slight positive, right? Yeah. And so what was going to go over here? The oxygen, right? And the oxygen is going to have like something's going to happen. Things are going to go down. Something's going to happen. That oxygen is going to become super unstable, and it's going to have like a crazy negative charge. And that is why chymotrypsin strategically placed glycine and serine, the NH portion right there to stabilize that super crazy negative charge. You have to know that. It might be on your test. It might be like multiple choice, and they'll try to trick you. So know your facts, okay? All right. Now, you know the importance of serine 195 and glycine. I think it's glycine 193. I don't know. I wrote it down for you on the side, the exact numbers, because you have to know the numbers, okay? All right. Another portion of this is called, let's review. We have the hydrophobic pocket where the phenyl group is going to go. We have the oxyanion hole where the oxygen from the carbonyl group from the peptide bond is going to go. And then we have these two little amino acid amines, NHs, that will help stabilize that negative charge on the oxygen at some point. Okay, then we have these three very special amino acids that together, they make up the catalytic triad. And that is one of your most important terminologies for this chapter. Aspartic acid, histidine, and serine make up the catalytic triad. They are responsible for breaking that peptide bond. So when they try to trick you on a test or a quiz and say, oh, water, because hydrolysis is going to go in and break that peptide bond. No, sir. It's aspartate, histidine, and serine that make up the catalytic triad that break that peptide bond in step 1 of chymotrypsin. Easy so far? Yeah.
What did you say, glycine?
So you tell me what is glycine doing? Look at all the charges. What's going on?
It's holding on to the water or to the oxygen.
Is it holding on?
Or-
Is it holding on? What is it doing? What is the word we use in biology? It is stabilizing.
Mhm.
It is stabilizing because it has that positive charge, and that oxygen, we haven't gotten there yet, but soon oxygen is going to have a crazy negative charge. So yeah, glycine is not a part of the catalytic triad. The catalytic triad is aspartate, histidine, and serine. Okay, so let me walk you through each step because it gets down to that level. Okay, aspartate. You see this oxygen and this hydrogen on aspartate, this hydroxyl group? Okay, oxygen has a partial negative, we know that. So this hydrogen will have a partial positive. Well, histidine is right next to it. It's like really close. And this nitrogen on histidine also has a slight negative. So the positive and the negative want to hang out. They get together. When they get together, things change. Okay? Histidine used to have a pKa value of 7. A pKa value is the pH at which that group wants to donate its proton. So histidine used to be really nice. And at a pH of 7, he was like, oh, take my proton. Just take it, right? But when that hydrogen and this nitrogen interact and get together, histidine turns mean. All of a sudden, its pKa value goes all the way to 12. It goes all the way to 12. So now it doesn't want to just give away its proton anymore. It's like, no, I don't want to give it to you. You need to have a pH of 12 in order for me to give you my proton. So it's kind of crazy now, right? So when something has a really high pKa value, another name for that is a Lewis base. And what do Lewis bases like to do? They like to take protons. So normally it's accept, but because the pKa value just rose like insanely, it is at a point where it is forcing protons away. It is literally taking them by force. Okay. So what it's going to do is going to take that proton from serine. So serine used to be all happy with its hydroxyl group minding its own business. But because histidine's pKa value rose all the way to 12 and he became a really strong Lewis base, he just like stole that hydrogen. And so what happens is this oxygen gets a really strong, it becomes a really strong nucleophile. That question, they love to put it on exams too. Who from the catalytic triad becomes a strong nucleophile? It's serine, because they stole his proton. So he became a really strong nucleophile. And what is he going to do? He's going to attack. He's going to attack who? He's going to attack this carbon on the carbonyl from the peptide bond. So he attacks this carbon. And what happens is that you get electron pushing. So you end up with one bond. So carbon, one bond, and oxygen. So we know that at this point, oxygen, this is the state that I was talking about. That oxygen that is in the anion hole, it only has one bond and it has a crazy unstable negative charge. So that is where glycine and serine are needed to stabilize. Yeah? Everything makes sense? It's not too bad, right? Okay, I'm gonna repeat it one more time. We have a hydrophobic pocket. That is where your phenyl group is going to go. We've got an oxy anion hole, and that is where the oxygen is gonna go from the carbonyl from the peptide bond, because it could be any carbonyl, but it's not, it's the one from the peptide bond. And what's gonna start this process is that your polypeptide chain will come in. And another thing that they can do for you on the test is they can give you like a longer chain, but they'll only give you one phenyl group. And you will have to know where, like you'll have to draw it out, like draw the line, where is the peptide bond that is going to be cleaved? And that's a very common question. So you have to know, here's the phenyl group. Well, here's my N, C, and C. So this is the carbonyl group that belongs to this amino acid. And so that carbonyl is attached to this nitrogen, and that is my peptide bond. So that's the bond that's going to be broken. And so they'll ask you, what are your products going to be? Well, this is product 1, and this is product 2. So it's a very easy question if you know how it works. That's why I'm spending so much time on this, like just the beginning of it. So, okay, so then that polypeptide goes into the active site of chymotrypsin, and everything goes where it's supposed to be, the phenyl group, the carbonyl oxygen. And then step 1, aspartate, there's like a slight conformational change that puts those groups closer together, and all of a sudden they can't resist each other anymore. That hydrogen at positive charge and that nitrogen negative charge, they can't resist each other anymore. They want to get together. So they do. And that makes histidine go a little crazy. And all of a sudden its pKa value goes from 7 all the way up to 12. And because of that, he becomes a Lewis base, which means that he is just going to steal protons like crazy. So, you know, serine's hydroxyl group happens to be nearby. So he's going to steal the hydrogen from serine. Serine's going to go a little crazy, the oxygen, and it's going to attack the carbon on the carbonyl from that peptide bond. You're going to get like a single bond here. That oxygen is going to have a negative charge, which is going to be stabilized by the NH from glycine and serine. And then when the electrons bounce back and you get that double bond again, that's when that bond is going to be broken, that peptide bond. And so once this peptide bond is broken, this product 1, this blue section, is released from the enzyme. But this other portion is stuck. It's stuck to the enzyme. So this is step 2. This is where your water molecule comes in. Your water molecule comes in and breaks the bond that is attaching the enzyme to this portion. So once the water molecule comes in and breaks that, it's not breaking a peptide bond. It is breaking whatever is holding the enzyme to the enzyme to this product. So then the product is going to be released, and then you'll be free. But on the test, they might ask you, you know, like, where does the water molecule come in? What does it break the peptide bond from the substrate? And you're going to say, no, it doesn't. Yeah, basically anything. Yeah. Yes. What? Does what? Does it always break in that order?
Yes.
Oh, as long, it all depends on this guy, wherever that guy's at. So you can have 10 amino acids, but wherever that guy's at, that's where it's gonna break on that next peptide bond. Yeah.
So if you have 3 phenyl groups in a row, you would have 2 free phenols. Basically 2 amino acids with phenyl groups free.
Oh, then it could, I don't even know if it would fit in here. It may be steric hindrance, like you might get steric hindrance and it may not even, yeah. So yeah, I have no idea. That's a good question. So all the terminology that I used today, like it's not enough. Okay, it was close to enough, but in the video there's more and you have to know all of it. So I was actually going to play the video for you and then walk you through, but it's not working. Like I need to shut down my computer down, I guess, because it's not working. But yeah, we'll just keep going for now. Okay, the catalytic activity of chymotrypsin is affected by pH, as shown in the curve. This curve is taken from figure 6-22 part B of your book. How can you explain this behavior? Consider the amino acids in the catalytic triad and suggest which step of the reaction would be most affected by this pH change. Okay, so here I ran out of time because I was uploading the videos and finding them and everything. So I just copied and pasted the keys that she gave you. So what you're going to be seeing on Friday, that's what these are. And I'm just going to like read and walk you through. Okay. So why is pH so important for chymotrypsin? And then they give us a graph right here. We have pH on the right. So pH goes from 6 to 10. And then the KCAT, that's the enzyme efficiency. So it's saying that we have a low enzyme efficiency at a pH of 6. But then as soon as we get to higher pHs like 8, 9, 10, then we have a much higher enzyme catalytic efficiency. That's what this graph is saying. So they're saying, why is pH so important? And the answer is that the catalytic activity is decreased at lower pH because histidine 57 will be protonated. A protonated histidine 57 wouldn't deprotonate serine 195. So that's why this is so important, right? If histidine has a proton, why would it go and steal? Like it can only hold one proton at a time. So why would it go and steal the proton from serine? It wouldn't, right? So that's why pH is important. Because at a pH of 7, or what did they say, 6? Whatever, at a lower pH, histidine has his proton. So that's why it wouldn't steal anyone else's. So at a higher pH, the activity of the reaction increases because histidine 57 is deprotonated. And it's able to remove the proton from serine 195. So serine 195 can become a strong nucleophile. So it's everything we already talked about. So given the 3 following reactions, A, B, and C, explain what kind of catalysis or mechanism, acid base, covalent, or metal. So this is another thing for exam 2, you have to know these types of catalysis, acid base, covalent, or metal. So I also have examples in a video that I linked. I think it's video number 3. And what amino acids can participate. So as a catalyst in each reaction. Okay, so basically for this kind of stuff, you need to have terminology and you need to have rules. So in the video, I go over all of that. And then I copied and pasted this table for you here. It's the International Classification of Enzymes. So you have 6 different classes of enzymes. You got to know them. You got the names, and then you have the types of reactions that they catalyze. So for me, I like to start from the bottom up because it's just easier for me. So ligases, formation of carbon-carbon, carbon-sulfur, carbon-oxygen, and carbon-nitrogen bonds. So anytime you see a reaction and you're like, oh, there's a new bond, then you know that that's a ligase. Easy, right? Okay. So it says these are condensation reactions coupled to, do you guys remember what a condensation reaction is? A water molecule leaves and a bond forms. Yeah. So it's just the opposite of hydrolysis. Remember that. Okay. And it says that it's coupled to cleavage of ATP or a similar cofactor. So that's another clue. If you're given a reaction and then You're like, oh my God, there's ATP and a new bond formed. That's definitely a ligase, right? Okay, cool. So now isomerase, transfer of groups within molecules to yield isomeric forms. Well, that's easy. If you have like 2 amino acids and on one of them you have like the hydroxyl group on the left, and then the other one you have it on the right, that's an isomer. So then you know that you have an isomerase. So that's a pretty easy one to identify as well. Those two are my favorites. Then you have a lyase. Now you're cleaving bonds. So cleavage of a carbon-carbon, carbon-oxygen, carbon-nitrogen, or other bonds by elimination, leaving double bonds or rings, or addition of groups to double bonds. So with lyases, you're breaking bonds. You're leaving behind double bonds or rings, or an addition of a group to an existing double bond. It's an elimination reaction. Hydrolases. These are hydrolysis reactions. You transfer functional groups to water. So whenever you see H2O and it's by itself, and then all of a sudden H2O has a different group attached to it, that's kind of how you know that that's a hydrolase reaction. Transferase, group transfer reactions. So there used to be group A, and it had this one, or let's say whatever had group A, and then all of a sudden this other thing has group A. That's a group transfer reaction. So then oxidoreductases, these are transfer of electrons. So you can transfer hydride ions or hydrogen atoms. Okay, so we have a couple of examples here. Okay, so for A, we have a nitrogen. Oh, I feel like I'm missing something. Okay, I wanted to give you another set of notes, but that's in the video. It's like another cute little box, and it tells you, like, it shows you the little N with the dots. Like, it shows you all of those, and it tells you what amino acids they belong to. So take notes of that in the video, because I'm not going to be able to add it here. Okay. So you have a nitrogen, you have an R group, 2 hydrogens, and then over here you have your R group 1, you have a carbonyl, CH2, and then you have R2. Okay, this is what you're starting with. And then the reaction happens, and then all of a sudden you have R1, and your oxygen is gone. Now you have nitrogen, bam, took its place. Okay, you got the R group, you got the hydrogen, and then you still have the CH2 and the R2. Then another reaction. All of a sudden you have R1, your oxygen is back, and now you have CH3. So your R2 was cleaved. So the first thing you have to do is like look at what you're starting with, look at the reactions that happen, and then look at your final products. You have 3 separate products now. And this one remained like identical. The only thing that happened is that the R2 was removed, but there was like an intermediate step. Okay, so now I'm gonna explain the answer to you. Okay, so the side chain of amino acids in the active site of the enzyme act as catalysts. Acid-base catalysis involves the transfer of a proton, often forming unstable transition states. Covalent catalysis involves the formation of a covalent bond. Metal ion catalysis involves a metal ion. Oh, sorry, I was giving you the definitions of the 3 types, my bad. Okay, so the answer is right here. This is a covalent catalysis reaction. During the reaction, the substrate gets covalently attached to the enzyme. So this guy right here, this is the side chain on the enzyme. And then this is the substrate. So during the reaction, the substrate gets covalently attached to the enzyme. The N in the side chain of the amino acid acts as a nucleophile, attacking the electrophilic carbon of the substrate. So remember, there's a carbon right here. So this nitrogen acts as a nucleophile and it attacks this carbon. So that's why the oxygen left. And it was replaced with this night. So this is a temporary covalent bond that formed in this intermediate state. And that is how you know that this is covalent catalysis. So the thing that attacks will usually have like the dots or a negative charge or something like that, and it'll attack, and then that will be called the nucleophile, and then whatever it's attacking will be called the electrophile. So know your terminology. So this intermediate decomposes, yielding the shortened carbonyl product. So this intermediate doesn't stay that way. It decomposes and then it yields that carbonyl product so that it just goes back to what it was. The side chain of lysine contains a primary amine that can catalyze this reaction. So yeah, if you guys remember, what amino acids had a positive charge with amines? It was like lysine and arginine, right? So this is what I mean. Like this stuff is just building on itself. You just have to know who does what. So that table that I'm talking about in the video, that tells you all the amino acids that have ionizable groups and what they look like once they donate their proton, so that when you look at this, you're like, oh, that is either lysine or arginine. You know what I mean? So memorize that table. It's small, so you can do it. Okay. Okay, but that was a really tough one. Are you guys okay with it so far? Kind of little practice. Okay. The next one. So here we have a water molecule. Okay, water molecule. We have a nitrogen, again with the dots, and two R groups. We have a double bond here. Okay, and then over here, we've got stuff happening. There's like electron pushing, right? We've got a methyl, carbonyl, oxygen, NO2, okay, and then we have a middle reaction. So the water is not here anymore. We have N with the two R's and then a hydrogen. Okay, so this nitrogen stole that hydrogen from the water. Okay, and then the oxygen with the hydrogen that was left over, they went and joined this molecule over here. Okay, and then your products, so this is the intermediate step. Those are your substrates, what you're starting with, intermediate step, and then what's left over. So at the end, you end up getting this guy by itself. So it's still there with the NO2 and the OH. So this group is going to be separate. So we have, okay, so the N with the R and the R, so that group stays the same. So that group stays the same. And then from the intermediate step, we have this guy. So this water molecule was just split up like between these two. So you can see kind of like where everything went. So the enzyme accepts a proton from water. Okay, so I guess this is the enzyme right here because it is stealing a proton. I consider it stealing. I guess it's accepting, whatever. It's taking a proton from water. This is your water. And the resulting hydroxide attacks the substrate. Yep, we saw that there. The OH attacked the substrate. Histidine can act as a base in its unprotonated form. So this is histidine, and that table will show you because it has this double bond to the R. And that's how you know that it's different from like this guy. Oh, class is over, you guys. It's already 9:20. Time just flies. Okay, I'm gonna stop recording and I'll go ahead and upload that for you guys if you need to see your notes, review the material.